Today we're going to look at the angle bisectors of a triangle. So what is an angle bisector? So an angle bisector, as we already know, is something that cuts an angle in half. So in this case, we can see that PS is the angle bisector of angle QPR. Now what that is going to tell us is that we know that this distance from Q to S is the same as the distance from S to R. Because if we're along that angle bisector, we should be equidistant from the sides of the angle. So that's what we're going to call our angle bisector theorem. So I would jot this theorem down, pause the video if you need to. So a point is on the bisector of an angle if and only if it is equidistant from the two sides of the angle. And you'll notice I reworded that a little bit here because the converse is true as well. And when the actual conditional statement and its converse are true, we can write that as a biconditional. So a point is on the bisector of an angle if and only if it is equidistant from the two sides. So looking at our picture here, it says find the measure of angle GFJ. Well, because these two distances are 7, we can safely assume that this is also 42. So the measure of angle GFJ is 42 degrees. For the next question, for what value of x is P on the bisector of angle A? So we're assuming that this is the angle bisector here, which means that x plus 3 should equal 2x minus 1. And if we solve for that x value, we end up with a value of 4. So taking a look at each of these on your own, find the value of x, and then unpause the video to check your answer. So we should have 15, 11, and 5. According to the diagram, how far is L from HK? So L is 27 units at its shortest path from HK, and so therefore we know it's the same distance to HF. How is ray HL related to angle KHF? Well, this is the angle bisector simply because we know these distances are the same. So we're going to call that the angle bisector. And then find the value of y by setting 6y equal to 4y plus 18. And if we solve that, we get a y value of 9. If we want to find the measure of angle KHL, then we just need to plug back in. 6 times 9 is going to give me 54. And FHL should also be the same. So that's a good way to check and make sure we've done that correctly. Now I would pause the video here and write down all of the key components of an angle bisector. The angle bisector will have a point of concurrency called the end-center. The end-center is equidistant to the sides of the triangle, and it will always, always, always be inside of the triangle. And what this will allow us to do, since it's the same distance to each side, is it will allow us to perfectly inscribe a circle inside of that figure. Again, pause the video here if you need it to jot down any information. We've gotten all of this written down so far, but this diagram is kind of nice to show what these are. So in this particular diagram, your angle bisectors are shown in red, and the congruent segments are shown in blue. So this point of concurrency for the angle bisectors is called the end-center, and it's always inside the figure. Because this is always inside, it allows us to perfectly inscribe a circle, which you can kind of see between the two pictures that we have here. So it says name the point of concurrency for the angle bisectors. So really what this is asking us to find is where is the incenter. So what I want to do is I want to look at each corner or each vertex and see if it's being bisected. So that one is, and this one is. So both of those lines are meeting at point Q. Same thing for number 11. I've got one angle bisector here, another one here. They're both meeting at point U. One here, both meeting at point X. And last but not least, one here and one here, both meeting at point Z. So in the diagram, N is the incenter. Find the length of ND. So I want to know how long this segment is right here. So remember that that's the same as this segment and this one, because the incenter is always the same distance from the sides. So if I look closely at what I have a right triangle where I have 16 and 20 as two of the sides. So what I'm going to do is I'm going to say x squared plus 16 squared should equal 20 squared. In other words, I'm going to use Pythagorean theorem to help me solve this question. Now if I start to solve and I subtract and do all of the components here that I need, I'm going to eventually end up with x squared equals 144. So when I take my square root of both sides, x comes out to be 12, which tells me that the length of NF is 12, and therefore so is ND and EN. So it says, in this example, suppose you were not given AF or AN, but you are given BF and BN. So if we look at that, that would give us a different triangle to look at right here, but our process would be the same. We're still going to use Pythagorean theorem. So in this particular question, you're probably going to want to get started with me and then pause the video to try this on your own. So it says find the value of x that makes this the incenter. So if the incenter is equidistant to the sides, that tells me that this is x minus 1. So I'm going to use a squared plus b squared equals c squared to solve. So x minus 1 squared plus x plus 6 squared should equal 13 squared. Where you want to be careful is x minus 1 squared is x minus 1 times x minus 1. Same thing for x plus 6. Hello. So we're going to make sure that we distribute that out correctly. So we've got x squared minus 1x minus 1x plus 1 equals x squared, or sorry, not equals, we should have a plus sign there. So plus x squared plus 6x plus 6x plus 36 all equals 169. Now at this point we've got kind of an ugly quadratic that we're going to need to try to clean up and see if we can solve. So if we combine our like terms here, we have 2x squareds minus 2x here plus 12x here. So that's the same thing as 10x's. And then we've got 1 and 36, which combine to be 37, equals 169. At this point, since this is a quadratic, I'm going to need to do some sort of factoring. And anytime I factor, I want to set this equation equal to 0. So to do that, I'm going to subtract that 169 from both sides. Now the good news is that all of these numbers are even. So I'm going to divide everything up here by 2 to make my life a little bit easier. And now I need to find factors of negative 66 that add to 5. I would recommend that you pause the video here, try to finish this on your own, and then come back to check your answer. So if I want factors of negative 66 that add to 5, I've got negative 6 and 11. So with that, since my a value is 1, I can jump using the shortcut to the final factors. So that tells me that x is either 6 or negative 11. I'm going to try to rewrite that because that looks a little messy at the end. So x is either 6 or negative 11. Now in this case, if that x value is negative, and I go back and look at some of these equations, that's going to make a negative distance. So negative 11 is not a valid solution, but 6 is a valid solution. Now this is a little bit of a tough problem. However, you know that we typically see factoring and systems on every test. So it is highly probable that you are going to see a question like this coming up. So keep that in mind. We're also going to very briefly talk about an altitude. An altitude is a perpendicular segment from the vertex to the line containing the opposite side. So what's the difference between an altitude and a perpendicular bisector? Well, we have the perpendicular part. What we're missing is the bisector part, meaning this segment does not have to be the same as this one. And another key difference is that it has to touch the vertex. Pause the video here if you need to take some notes. So the point of concurrency for all of the altitudes is going to be called the orthocenter. This point can be inside, on, or outside of the triangle. So in an acute triangle, it's inside. For a right triangle, it's at the corner of the 90-degree angle. And for an obtuse triangle, it's outside the figure. So what I'm looking for here when I'm looking for the orthocenter is I want to try to find the altitudes. So I've got one altitude coming down from this vertex perpendicularly here, and I've got another perpendicular here that's connected to this vertex. So my orthocenter is at point H. Same thing here. I've got one altitude, so my orthocenter is at point Y. When I'm looking for the orthocenter, remember that those are formed by the altitudes. So what I need to do is form a perpendicular line from a vertex to the side across from that. So with this one, I can very easily sketch one of my altitudes right here. However, the other sides are going to be a little bit trickier. So what I want to do is I want to look for the slope of one of the other two sides. So from B to A, I've gone up 8 and right 4, which means a rise of 8, run of 4 is a slope of 2. So if I need a perpendicular slope to that, I need a slope of negative 1/2. And I need that perpendicular line to connect with C, the vertex across. So from C, I'm going to go down 1 and right 2, but that would go off my graph. So I'm going to go up 1, left 2, up 1, left 2, up 1, left 2. So I can see where those two altitudes are intersecting. So my orthocenter is right here at the coordinate 6, 4. Since this is a point of concurrency, I don't need to create the altitude for the other side, but I could if I wanted to. Thank you so much for your time today. If you have any questions or concerns, please feel free to reach out via email. Have a great day.